I'm Professor Rad, and this is Precalc video 1-10, Extrema. So in this video, we're going to be talking about maximum and minimum values of a function. So we're going to have kind of sort of a general definition for what a maximum and a minimum is, and then we're going to break that down into some more particular subgroups of maxes and mins. So if you want to take a moment and copy down these definitions, then we'll talk about them and we'll do some examples, of course. So hopefully you've got those definitions written down. If not, pause and write them down. Okay, so f of x has a maximum value of f of a when x is a. If f of a is greater than or equal to f of x for all x, and this is where things can change a little bit depending on if we're looking at the whole domain of the function or if we're looking at an open interval. Similarly, f of x has a minimum value of f of a at x equals a if f of a is less than or equal to f of x for all x. In other words, if you have a function and there's a y value that's bigger than all the other y values, it's a maximum. F of a is the y value and it is bigger than all the other y values. That makes it a maximum. It's a minimum if it's smaller than all the other y values. So if f of a is smaller than all the other y values, then that's a minimum value. So as I sort of alluded to, these definitions are sort of dependent upon where we are looking. So if you're looking at the domain of the whole function, that's going to be an absolute maximum or minimum. And if you're looking at only within like a small window, a small region, that's going to be what we call a local max or a local min. So I'm going to erase the board and write down some identifying characteristics of both of those things. And then you can pause the video and copy those down for yourself. And we'll talk about them and then we'll get into some examples. And poof, just like that, there's like the whole novel on the board here. So if you want to pause and copy this all down, feel free to do that. Or if you want to screenshot, whatever's going to work best for you. In this case, I'm just going to read through them. So in red here, I have information about the absolute extrema, so absolute max and min. And here I have information about local maxima and minima. So an absolute maximum or an absolute minimum is a maximum or a minimum value across the whole domain of the function. So where is the highest point this function will ever reach? Where is the lowest point it will ever reach? You could have an endpoint value be an absolute max or min. So if your domain is a closed interval, let's say it starts at a point here, ends at a point here, right? So it's defined on a closed interval, and this is the highest it reaches, then that could be an absolute maximum. You might or might not have an absolute, you may or may not also be a local max or min. So an absolute max could also be a local max, but it doesn't have to be, it might not be. Similarly, an absolute minimum might also be a local minimum, but it doesn't have to be. And lastly, your function may or may not have an absolute max or an absolute min. So we're going to look at some examples of where these weirdnesses can happen, don't worry. But just know that when we're looking for extrema, you can get some extreme stuff happening, or not so extreme if you don't have one, I guess. So for our local maximum and minimum, these are max or min values that are not over the whole domain, they're over open intervals. So remember, an open interval is where you don't include the endpoints of your interval. So as a result of that, they cannot be endpoints, because if you have an endpoint, there's no like open side behind it. It's the beginning of a closed interval. So as a result, local max or min cannot be endpoints. And so basically what we're looking for here, let's say you've got a function that does this, right? It's got lots of hills and valleys. So the absolute tallest hill, that's an absolute maximum. But the smaller hills, they're still hills in their little region. So they're still hilltops. So they are local maxima. Okay? Same thing with the valleys. The deepest valley is your absolute minimum. And then you might have some valleys that are low, but not quite as low as the absolute. So those are your local minima. Once again, your local max or min may or may not also be an absolute max or min. And your function may or may not have a local max or a local min. So a function doesn't need to have any of these. It could, and it could have them in any kind of overlap or combination. So because we can get lots of weird stuff going on, we're actually going to look at 2 examples of Extrema. And so let's put the first one on the board and we will look at it. Okay, so here's our function f of x. To graph this, I only needed positive x values. So I started at 0, excuse me, and went over to 10. And then for my y-axis, I went from -4 to 4. The specific points that it goes through the point 0, -2, to 1, 4, -1, 5, 1. Then we have an open circle here at 6, 4. And then it looks like 10, 2. It has a nice cusp here at this turning point. So notice that it is a sharp turn there. It's a little bit more, well, it's still not even smooth here because it's got concave down or concave up and concave down. So this is a very peculiar function, y'all. All right, so let's talk about its extrema. So when I find absolute max and min, I look at the whole function and I say, where's the highest point? Where's the lowest point? So one thing to notice is this function doesn't have any arrows. So its domain doesn't include -infinity or positive infinity. So it's kind of bounded for its range and for its domain. When I look for the absolute highest point, it looks like it's going to be at this open circle here. But we have a little problem. So because this is an open circle, that means my y values are going to get infinitely close to 4, but never get 4. So we could have 3.9, 3.9999, 3.1000 nines, followed by a 2, right? So we can get super close to 4, but we're not going to reach it. What that means is this function does not have an absolute maximum. And that's because it never reaches that tallest y value to give it a maximum. Now, absolute max and min, we said could be endpoints. So you might be wondering, well, why isn't this the absolute max then? And the reason this point is not the absolute maximum is because there are y values on the domain bigger than 2. This has a y value of 2, and these over here have y values super close to 4. So there's no point on this function, no y value that is greater than all other y values. However, there are places where we have smallest y values. So if I look at my y values, the smallest one appears to be here, right? So this was the point 4, -1, and this one's 0, -2. So -2 is the smallest y value that this function has. So we would say we have an absolute minimum of -2. Now, remember when we did our intervals of increasing, decreasing, and constant, we were only really interested in the x values? Now the opposite, we are interested in the y values because the y value is telling us the actual max or the actual min. So here we have an absolute minimum of -2 because that is the smallest y value we will ever reach. If you wanted to be more specific and identify where it reaches that absolute minimum, you could then also say an absolute minimum of -2 at, in this case, x equals 0. So you could indicate where it is happening, but when we state the minimum, we just want the y value. I'm mentioning this because maxima and minima are numbers. They are not ordered pairs. So if you were to write a minimum as an ordered pair, if you were to write the coordinates of that point, this would be wrong. So the minimum is not the ordered pair. The minimum is the y value of the ordered pair. So we want to make sure we're being precise in how we are expressing our values. Now for local max and local min, they may or may not exist on this function, and they may or may not be where, well, in this case, where the absolute min was. So to find a local max, I want to say, is there any mountain, may not be the tallest mountain, but is there any mountain for this function? And here we have a small one. So if I just ignore what's going on with most of this function, and I just look at this little piece that's remaining, it looks like it has a peak here when x is 2 and the y value is 1. So that means we have a local maximum of 1. If I lived in this neighborhood, in this region, then this would appear to be a maximum value. So we have a local maximum of 1. And again, you could be more specific and you could say at x equals 2 if you wanted to, but just identifying the maximum, we would just say it's 1. Nowhere else is there a local mountaintop. We do have a mountain here. This is a disturbing mountain because once you reach the peak, you vanish, right? There's no y value here at 4 because it's an open circle. So again, because we have an open circle, it is not a local max because we don't actually achieve the y value of 4. We just get infinitely close to it. To identify the local minima, now we want to see, are there any valleys? Are there any low points in this function? Now we had an absolute minimum here when x was 0. We have a minimum of -2. However, this is one of those places where we have endpoint being important. So for an absolute max or min, those can include endpoints, and the minimum was an endpoint. For local max and min, they cannot be endpoints because they have to be defined on open intervals. And in order to include this point, I have to include the end. So it has to be a square bracket, so it has to be a closed interval. So although this is an absolute minimum, it's not a local minimum. However, here we have a low point. So if I'm only looking now at this piece of the function, it looks like we have this little valley at 4. So the y value there is -1. So we have a local minimum of -1. And you can be more specific and say when x is 4 if you wish. And then, although this is a low point, right? So if I'm just looking now at this piece, this is a low point of the function. However, it doesn't, it's an endpoint, so it can't be a local minimum. And it's not an absolute minimum because 2 is not the smallest y value on the whole domain, -2 was. So we only have one local minimum as well, and it happens when x is 4 and the local minimum is a -1. So that's our first example. We get all sorts of weird things happening. Let's look at another example where perhaps some more weird stuff is going on. Alrighty, for this example, we're going to be looking at the function g of x, which is graphed here. G of x has a horizontal asymptote of y equaling -2. So you can see on the ends here, the arrows indicating that this function approaches -2 from above. It goes through the points -4, 0, -2, 4, 0, 3, 2, 3, and 4, 0. So if you wanted to take a moment and pause the video to copy down this function, you may also try your hand at identifying the absolute max, absolute min, local max, and local min, if they exist. So go ahead and try and identify those. And then when you've got them, unpause the video, and I will have some answers on the board and talk about how I found them. Alrighty, let's see how you did. So I have an absolute maximum of 4. I found that there was no absolute minimum. There is a local maximum of 4 and also 3, and there's a local minimum of 3. Does that sound kind of weird? So here's where those are coming from. So the absolute maximum is 4, happens here when x is -2. So if I look at the whole function, this is the absolute tallest point it will ever reach. And this time it was a filled in point, so we actually did reach 4. So the absolute maximum is 4. Because of this horizontal asymptote, we approach -2 from the top, but we never reach it. So we never have an absolute minimum because our floor is this asymptote that we never reach. So there's no absolute minimum value. For the local maxima, we have 4, but also 3. So let's see why that's happening. To get the local maximum value of 4, imagine just this piece of the function that's left open. So we have this little hilltop, and at the top of the hilltop, we have this filled in point. So we have a local maximum of 4. So here's an instance where a point is both an absolute maximum and a local maximum. So it's absolute because it's the biggest on the whole function, and it's local because it's the max within a closed or an open interval. Now, what may be weird are the local max of 3 and the local minimum of 3. That's kind of strange. So if you go back to our definitions of maxima and minima, we had for a maximum that f of a was greater than or equal to f of x, and for a minimum that f of a was less than or equal to f of x for all x in a particular region. So because we defined these not as strict inequalities, but permitting that equals, that means whenever you have a constant section of your function, you're going to get both a local max and a local min. So because of this constant piece here, if I were to look at this open interval of x values, if this was all I saw, then every x value here is both greater than and equal, or sorry, every y value in there is both greater than and equal to all the other y values and less than or equal to all the y values. So here we are achieving both a max and a min. So that's how we get our local max and our local min. Weird, I know. So when you have a constant section, just be on the lookout for that. Could be a local max and a local min. If this function never got any higher than that, it could also have been the absolute max, but this function did go a little bit taller. So the absolute max did not happen on that constant interval, but it could have, there's nothing to prevent it. So I know there was some weird stuff that goes on, but hopefully this helps with identifying absolute and the local extrema. In the next video, we're going to be talking about the extreme value theorem, which kind of talks about, it's a cool theorem as a result of increasing, decreasing, constant, continuous, and these extrema. So I look forward to seeing you there. In the meantime, have a wonderful day. Bye for now.